Hi, I am Kaan Keklikoğlu from Electrical and Electronics Engineering Department, and today I am going to talk about my physics final lab experiment. In this lab session for Physics 101, I investigated one of the simplest systems in classical mechanics, the simple pendulum. My objective was to measure the oscillation period of a pendulum and use that information to calculate the gravitational acceleration in my environment. Despite its simplicity being a mass suspended from a rope, the pendulum provides a reliable method for determining gravity. Throughout this experiment, I will briefly review the theoretical model governing pendulum motion, record its oscillations using a camera, and analyze the footage frame by frame to obtain precise measurements of its period. By comparing my measured values with the theoretical prediction for a simple pendulum, I will compute an experimental value of G and discuss the physical and methodological factors that contribute to measurement error. Detailed derivation can be seen on report, but to simplify, I use Newton's second law in angular form on the mass to obtain a differential equation. Upon solving the equation for angle theta, I find out that the solution is a periodic function only dependent on the gravitational acceleration and the length of the rope. So, if we can measure the period and length of the rope, we can find out G. For the experiment, a mass of 52 grams and a rope of 40 centimeters was used. The camera was stabilized sturdily in place and the pendulum was released with a small angle theta. After the recording, footage was inspected on a computer to determine the periods. Frame numbers of when the pendulum was in the starting position were recorded. Since the footage was 30 fps, dividing the frame numbers by 30 gives the time. Therefore, we can see that it takes an average of 1.3 seconds for a full swing. After running through the calculations for 3 instances of the experiment, 3 different G values were calculated, ranging up from 0.4% to 10% error. It can be seen that we got results reasonably close to the actual G, but still had an important margin of error. This was due to a couple of factors: insufficiency of 30 fps footage and air friction. To avoid those, we should have conducted the experiment in a vacuum. Also, a higher frame rate camera could have been acquired. Overall, the close agreement between the best experimental value and the known value of G supports the validity of the small angle approximation and illustrates the effectiveness of video-based measurement techniques in reducing human timing error.